Hello and welcome to Explore Classroom. My name is Ashley Holmes, and on behalf of National Geographic Education, I'm so happy to see you all today and welcome you to another Explore Classroom. Let me just pin my video. National Geographic believes in the power of exploration and wonder to change the world. The heart of our National Geographic community is, of course, our National Geographic explorers. Explorers are cutting-edge scientists, amazing researchers, and powerful storytellers. These Explore Classroom events connect students around the world with our National Geographic explorers for short lessons and extended Q&As. We are now hosting Explore Classroom every weekday at 2 p.m. Eastern Time, in addition to the usual events. So if you'd like, you can see you right back here on Monday. Today, we are very lucky to be connecting with Julia DeMarines. Julia uses giant radio telescopes to search for intelligent life in the universe, which is crazy. This process is also known as SETI, or Search for Extraterrestrial Life, but she'll tell you way more about that. Today, she'll help us marvel at the size and scale of the universe and celebrate all things space, science, and astrobiology. But before she does that, I'd like to acknowledge that we're joined on screen by several student groups, and we have over 1,000 students registered to watch online today. I'm so glad to have so many of you with us. We have groups joining in from around the US and around the world. It's a long list, so bear with me, but we have students from Bosnia and Herzegovina, Canada, France, Hungary, Ireland, Mexico, Peru, Romania, the United Kingdom, and Uzbekistan. And then in the United States, we have students from Alabama, Alaska, Arizona, California, Colorado, Delaware, Florida, Georgia, Illinois, Iowa, Kansas, Maryland, Massachusetts, Michigan, Nebraska, New Jersey, New York, North Carolina, Oklahoma, Oregon, Pennsylvania, Texas, Utah, Virginia, Washington, Wisconsin, the US Virgin Islands, and Washington, D.C., where our National Geographic headquarters are located. There are a couple of special groups I also want to give shout outs to. Black Rock Elementary, Blackwood Elementary, Castle Elementary, Cousin Campus, Forest Lane Community School, Montessori Middle School, Lighthouse Dunes Academy, Lincoln Magnet School, Nashoba Brooks School, Park Maitland, Pima Partnership Academy, Pioneer Elementary, the Young Earth Space Scientists, or YES Academy, Two Brothers Academy, Willard Kinsey Environmental Education Center, and Yuba Environmental Science Charter Academy. Now that was a lot, and I'm sure I missed tons of you, so please say hi in the chat bar and let us know where you're watching from today. But that is plenty from me. It's finally time to turn it over to Julia for today's Explore Classroom lesson. So Julia, go ahead and take it away.
All right, hi everyone. I'm gonna go ahead and share my screen. It's so exciting to be here with you all. I love talking about life in the universe and how we're gonna find it, and that's what we're gonna be talking about today. So I'm just going to go ahead and share my screen and make sure that this is coming through. Can I get a thumbs up if that is working?
Yeah, it looks great.
Awesome. Okay, so searching for life in the universe. Okay. So I'd just like to acknowledge the institutions that I'm a part of. Blue Marble Space and Berkeley SETI Research Center. And we also run a program called Ad Astra Academy that was funded by a National Geographic Explorer grant. Oops. Okay, so I consider myself an astrobiologist, and I just wanted to ask you all, well, what is astrobiology? If you think you know the answer, go ahead, type it into the chat, but I'm gonna go ahead and just give the brief definition of what astrobiology is. NASA defines it as the origin, evolution, distribution, and future of life on Earth and in the universe. So let me tell you a little story about a cosmic traveler. This is a hardy spacecraft named Voyager, and there are actually two of these spacecrafts launched in 1977, Voyager 1 and Voyager 2. And this little spacecraft took advantage of a planetary alignment where it could slingshot on the gravity of the planets to get to the outer solar system and take some of the very first images of these outer planets. And it was traveling really fast, and it's still traveling now. But around 1990, it turned its cameras around and took a picture back home. If you can see it here on the right side, I'm going to highlight it for you. This is a photo of Earth from beyond the orbit of Neptune. This is, we call it the pale blue dot photo, and it's one of the most, at least to me, one of the most inspiring photos. And I'll tell you a little bit why. Well, first we can see the color of Earth. It looks bluish, and we're going to talk about why that's important later. But let's take another look at that 1 pixel of light there. You know, that represents all of us, our whole entire planet, our history. There's a whole monologue by one of my favorite scientists, Dr. Carl Sagan, who talks about the pale blue dot and why it's important. So to understand why this pale blue dot photo is so important and why we're looking for other pale blue dots out there, we're going to take a big jump into the kind of what the universe is, how big it is, and how we're going to find life out there. So I have a bunch of slides to throw at you. I'm going to try and go through them fast. But again, sorry, this is my favorite topic and I could talk for hours about this. So I want you to first get your brain warmed up. How to detect life out there? What do you think? Are we alone? How are we going to do this? Maybe you know something about life detection or exoplanet detection. But today we're going to talk a little bit about habitability, life in the solar system, exoplanets, detecting life, and SETI. So to answer the question of are we alone, we have to understand the scale of the universe. You know, space is really, 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 really big. And I want you to take a look on your screen and guess what those blobs are kind of flying at the screen. Some people shout out stars, some people shout out galaxies. If you guessed galaxies, you are correct. And we live in a galaxy called the Milky Way. This is not our galaxy, this is another galaxy. It's hard to take a photo of our own galaxy while we're in it. But we live about 2/3 from the center around a small star, or about here. So the universe is a collection of, it contains all space and time, contains everything that we know. And when we zoom in to the universe, we see galaxies. And there are different kinds of galaxies. If you've never heard that word before, galaxy is a collection of stars and gas and dust. And there are different kinds of galaxies out there. Some are spiral, some are elliptical, and we live in one called the Milky Way that looks like this. When we zoom in to our Milky Way, when you go outside in the night sky, you see stars. And there are many different kinds and colors of stars out there. You might see kind of reddish ones, orange ones, yellow, white, and blue stars. And all of these stars, the color can actually tell you a little information about that star. Some of the bigger ones on the right, we call those O-type stars. They're huge and they burn really hot. And some of the ones on the left side, they're dwarf stars, like an M dwarf, the little orangey red one to the very left. Now I want you to just take a guess, which kind of these stars is our star? I'll let you think about it for a second. We live around what we call a G-type star, which is kind of like a small yellow dwarf star. So our star is not all that big and impressive, but we're really lucky to have the star that we do. And of course, around stars are planets. And we, as astronomers and astrobiologists, we're curious if there's planets around other stars. So the distance from the sun to the other planets is vast. And it's hard to capture this in a single image. You can see that the sun to the left is the sun isn't really to scale, but the little planets are the inner rocky planets. And you can see Jupiter and Saturn and Uranus and Neptune are way off the screen to scale. So it's hard to really capture how far away planets are from their star and how small they are compared to their star. And I know that the folks at National Geographic will send out 2 links for you to watch some videos to really understand the size and scale and how far away things are, because it's important to understand why it's so hard to find exoplanets, why it's so hard to travel to these planets, and even in our own solar system. and just to understand how small we really are in the context of the universe. So space is really, really big, as I mentioned. And I just want to pause here and have you take a guess on how many galaxies you think there are in the universe. We just learned that galaxies contain stars. There's many different kinds of stars, but how many galaxies are there out there? If you're joining us on the chat, go ahead, maybe type in a guess, or just think of one in your head. So there are about 400 billion galaxies out there in the universe. My next question is, how many stars do you think are in each galaxy? There are about 400 billion stars in each of those galaxies, give or take. These are all rough numbers. Some galaxies are smaller, some are bigger. So that's a lot of zeros to deal with. That's a lot of celestial objects to think about. But how do we find something that is similar to Earth? How do we find something that has a habitable condition? So we're going to take a look closer to home, and we're going to investigate our solar system. So I mentioned that there are different kinds of stars out there. The bigger, brighter ones burn hotter, and the smaller, cooler ones burn this kind of yellow or red and orangey yellow colors. So there's a region what we call the habitable zone that exists when you're not too close to your star and not too far away from your star. You kind of want this nice temperature where you're just right, kind of like sometimes call it the Goldilocks zone, you know, with the porridge, where it's just right temperature to have liquid water. Of course, there are more factors that you need to have liquid water on a planet. And why is liquid water so important? Well, every single place on Earth that we find water, we find life. And scientists believe that water is a key ingredient to finding life out there. We believe it's something that all life requires. So if we think about the habitable zone, this distance that's not too cold, not too hot, it's represented by this blue ribbon. So you can see that Earth falls right into that habitable zone. And if you have one of those smaller stars, your habitable zone will have to be closer to the star because it's not emitting as much heat as, say, our star or even a bigger, brighter one towards the top here. So if you're one of these bigger stars, your habitable zone will have to be farther away. So just some things to think about. Now, this is the most graphy graph I'm going to put up today, but this is going to explain why when we look for life in our solar system and beyond, why we really want to find liquid water and how hard, what kind of other things we need just besides the right temperature. So on the left here, we have pressure. So when you think of our atmosphere, it's actually holding kind of, it's like pressure on top of us. Have you ever dove down into a swimming pool and you feel your ears hurt, or gone up in a plane and also feel your ears hurt? So you're noticing that change in pressure. So this is what we call a phase diagram of water. We have solid, liquid, and gas or vapor. And the way you get the different phases, solid, liquid, or gas, depends on the pressure and the temperature. So our atmosphere has a pressure of about, we call it 1 atmosphere. And it's this line right here. So Earth sits here, and we have a temperature range kind of in this area. So we have a lot of liquid water on our planet, and that's because we have a nice atmosphere giving us pressure. And we also have the right temperature range. But a lot of people are interested in going to Mars as a place to look for life. But let me tell you something a little bit about Mars. Its atmosphere is 1% of Earth's. So it sits down here, and it's much colder. So it doesn't have a lot of the right conditions to have liquid water on its surface. But perhaps just like when you dive down into a pool, a swimming pool, you feel that pressure. Maybe if you go down deep into Mars, you could find the right enough atmosphere to have liquid water on Mars. But as far as we know, we haven't found any real liquid on the surface. So we're going to talk about a few other places in our solar system to look for life. I'm going to go through these pretty fast. The first place is Europa. an icy moon of Jupiter. And it's got this beautiful ice shell with these kind of crisscrossy stripes. And we're going to take a zoom into those stripes. I did this with a class and they said that these looked like spaghetti. So these spaghetti cracks are what's on the surface of Europa. And it's super interesting to see these cracks because it means that there's something happening underneath to reform the ice, to make the ice cracks like this. And it's most likely that there's a liquid water ocean underneath the ice of Europa. And that's super interesting because liquid water, that's great for life, for looking for life. So scientists believe it might look like something like this, perhaps a big, thick ice layer kind of holding in that pressure, a lot of water down here, and a rock interior, kind of like the core of Earth. So we know that here on Earth, we have whole ecosystems that don't interact with the sun underwater called hydrothermal sea vents. When we go deep down to the bottom of the ocean, even when there's no sunlight, we see these hydrothermal sea vents are kind of like underwater volcanoes. They're shooting up hot liquid water, and they have the right conditions to support these exotic ecosystems with tube worms and these crazy crabs. So who knows, maybe there is something like this under the ice of Europa. The next moon that we're going to talk about is Enceladus. It's a moon of Saturn, and it again has these cool stripes, these crisscrossy areas. We call this the tiger stripe area, and it's super interesting what's happening at Enceladus. There's liquid water geysers coming out of these tiger stripes. And you can see it here. This is an image of the water geysers coming out of the South Pole of Enceladus. And that's super cool. We're just seeing evidence that there's liquid water that's far, far away from the sun that might be a place for life. And I just wanted to mention that Mars is still a good place to look for life because perhaps in Mars's past, it had the right conditions. But let's get on. I don't want to talk for too long, but life beyond our solar system, how do we detect exoplanets? So an exoplanet is a planet that is not orbiting our star. So that could mean orbiting another star, and we're trying to find them. And as of today, this is a little bit of an outdated slide, but we have over 4,100 confirmed exoplanets, and we keep a tally. And we've discovered over 4,000 exoplanets in the last 20 years or so. So when I was your age, if I were in middle elementary school, we didn't have hardly any discovered. So it's a cool time to be an astronomer because this is some groundbreaking research that's happening. We're going to talk briefly about how we find exoplanets. There's 3 ways that we can find them. There's others, but these are the 3 ways that I'm going to talk about: radial velocity, transit method, and direct imaging. So the first way is the transit method, when you have your star and a planet goes in front of the star, taking away some of the light. So this is an image of our star. I took this with my cell phone in 2012, and we're observing a transit of Venus here. So if you want to think about this as a picture on your phone, you can imagine the sun as a bunch of pixels, right? And the transit of Venus going across the sun is taking away a handful of those pixels. And that's what we're looking at around other stars. And if you can imagine, when you look outside at stars are so far away that you think it might be really hard to notice a few tiny little pixels being taken away by an exoplanet. But in fact, our technology has gotten so good that we are able to do this. And that's super duper awesome, in my opinion. Just to show you what it looks like, here's a star with 2 different kinds of planets going in front of it. One, a small planet, and you can notice the brightness just dips a little bit. But with a big planet, the brightness dips a lot. So it's easier to detect big planets going around its star, and especially big planets that orbit really close to its star. which when we think about it, those aren't, as far as we know, probably the best places to look for life because we're looking for small rocky planets. So we're not really looking for these big gas giants. We're looking for these more small rocky planets. We found a few of them, but we still need to do a lot more searching. The next method is the radial velocity method. You can call it the wobble method or the Doppler shift method. But did you know that planets tug on their stars just a little bit? So our star is actually being tugged by the orbit of Jupiter, and it's making our sun wobble, do a little wobble dance. And we can detect that wobble of the star by using its light and examining its light. Actually, I'm going to skip this video, I think. Actually, I might do a little demonstration if that's okay. I'm going to and
Whoa, very exciting, Julia.
I forgot about all my fun tricks. Okay, so I've made this Doppler shift ball. It might hit my plant behind me, so I'm going to move this. It's going to make a sound, and I'm going to wobble it, and I want you all in the audience to see if you can hear the change in pitch. It's going to be very subtle. Did y'all hear it?
Very faint, but I could hear it. We'll see if the chat could hear it or not. Very cool.
Okay, we're back. Let me share my screen again. Okay.
Perfect.
So you probably heard a Doppler shift or that change in pitch when an ambulance or a car drives by and you hear it go, rear, rear, rear. And that's because the sound waves are being compressed when that vehicle is coming towards you and being elongated when it's leaving you. And we call that, not when we're not relating it to sound, to light, we call it blue shifted when it's being compressed and red shifted when it's being elongated. Because we can't hear sounds in space, but we can see light, and light waves do the same thing. Let's see, so this is just an image that our sun is wobbling. So this is the center of the sun, are all these little black dots and how they've moved over the years because of Jupiter. And I just think that's so cool that our star is doing this dance that, we don't notice it when we look at it, but it's really moving. So if you have a little planet, like an Earth-sized planet, it's only going to make the star wobble just a little bit. But if you have a bigger planet, it will make it wobble a lot. And I was mentioning the blue shift and the red shift. When we look at the light of a star using like a fancy prism, we see the rainbow. When we look at that rainbow a little closely, we see these spectral lines. And I'm going to get into these a little bit later. This is kind of an advanced concept, so bear with me. So basically, these are the colors, the elements that the star is burning. And we know that these lines should all be at a certain distance. We know there should be one in the red, and we know it's this far away from the one in the yellow. But when we see them shifted, we know that we're seeing that Doppler shift, that wobble, and it's making those lines move. So we can tell the speed of the star wobbling by how much those lines have moved. So here's that rainbow at the bottom, those spectral lines. And again, I'm going to go into those lines in a little bit. We can see as a planet is moving around its star, how that star is wobbling and how the light from the star is shifting with those spectral lines. So that's how we're able to detect exoplanets. That's one of the methods. The next one is direct imaging. So actually, I'm going to stop sharing my screen one more time and shine a bright light at your face. So if I'm a star, it's really bright, it's hard to see tiny planets next to the star. But when I block out the light, it's much easier to see the planet. But stars are really bright and they're shining and it's hard to see planets going around them. So we need to send something into space to block the light out of the stars to see the tiny exoplanets. And I'm going to be talking to you about a technology called a star shade, which looks like a giant sunflower. Oops, I just lost my planet. Oh, there it is. And I'm going to show you how putting a flower in space is going to let us see exoplanets. And to me, that is super cool because remember back to that pale blue dot photo? We want to find those pale blue dots. Okay, let's share the screen again. There we go. Okay, so we do have the ability to image exoplanets, but it takes a lot of fancy tricks to be able to do this. Now, this is a little video taken by some researchers at UC Berkeley. They blocked out the light of the star in the center. You can see the black disk. And these are actual planets going around another star. Now, these planets are very, very far away, kind of probably beyond, if we were to make this our solar system, beyond the orbit of Saturn. And they're very big, like the size of Jupiter and Neptune-sized planets. So we can see these giant planets far away from a star, but we can't see the ones closer in perhaps this star's habitable zone. So although our technology is getting better all the time, this one was taken from the ground, a ground-based telescope. So remember we were talking about the pale blue dot image? We want to directly image these exoplanets because we're interested in the color of the planet. We want to dissect that color. We want to put it through a prism to see what's inside of the atmosphere. And we're hoping to be able to do that with some of these larger telescopes coming up. For example, we have the Hubble orbiting Earth right now. And hopefully soon in the next few years, we're going to launch something called the James Webb Space Telescope, which is much bigger than the Hubble. And beyond that, a telescope called the LUVOIR telescope. And there's a few others that are hopefully going to go up too that can help us directly image these exoplanets. So this is LUVOIR, a concept mission by NASA. And we're hoping to use one of these large telescopes to pair with one of these star shades. And I mentioned this flower shape. I'm going to talk just a tiny bit about it. But you ever heard of those Bose noise canceling headphones? Well, the star shade is kind of like a light canceling, not headphone, light canceling technology. The light that goes around the edge of the petals deconstructively interferes with itself. And that, if that means nothing to you, that's okay. Just think of it like when you're learning about waves, when you have a crest and a trough coming together, they cancel itself out. So the light going around the star shade is doing that to itself. So it's canceling the light out of the star, and it's doing it much better than if we were just to put a circle. And we're hoping to find, this is kind of another complicated image, but we're hoping to fly this in space. This star shade will be about 50 meters. We're hoping to fly a telescope in the shadow of that, blocking the light out of the star and allowing the faint light of the planet to go into the telescope. And this bottom image here is what a simulated Earth might look like. So we're blocking out the star. We're having some glow here from dust around the star, but we see this pale blue dot. And that would be a super cool day if we were to get a pale blue dot image of another planet. And here's a concept of how that would look. So you unfurl this star shade like this. And believe it or not, NASA hired an origamist, someone who does origami to help with the folding and packing and deployment of this star shade. And I just think that's so cool, bringing art and science together like that. So hopefully one day when you all become scientists, you'll be able to work on a mission like this, because that would be so cool. All right, so that pale blue dot image, why I think it's so cool to have an image is because of rainbows. If we look closely at a rainbow that is coming from, let's say this cool gas is an atmosphere and the light passing through it is from its star, we see these lines, we call these absorption lines. And those lines tell a story of what elements are in the atmosphere. Now we know our planet has a different atmosphere than Venus, than Mars, than Jupiter. And we want to figure out if there is another atmosphere out there that's maybe similar or different, like Earth is. We have oxygen, we have carbon dioxide, we have nitrogen, and we know oxygen comes from plants. So we're trying to find something out there that cannot be explained except for by life. And I mentioned every element has its own lines. So they're like a fingerprint. And depending on the element, the lines are in different locations and they're spaced differently apart. And we have a really good idea. We know exactly where these lines should be. So we want to go out there and we want to look into these atmospheres of these exoplanets. And this is like a real scientific image. So here's a picture of our star. You can see our star's spectral lines of hydrogen. And when we graph it, it looks like these dips. You can see the dips line up with those black lines. So I want to show you what our atmosphere looks like when we graph it. So our atmosphere, we have dips of oxygen and water and ozone. So we want to find something that has these dips that look like maybe Earth or maybe something that's similar. Now let's talk about aliens. So we've just talked about how we're going to find life around exoplanets and perhaps life in our solar system. But what about signs of technology or signs of intelligence out there? So we've been, you've probably all seen E.T. E.T.'s trying to phone home. Maybe we can intercept an E.T. TV show or phone home or radio station as a sign of life out there. So we've been using radio waves for at least the last 100 years. And those radio waves can travel through space. And we can pick them up using powerful radio dishes like this one in West Virginia. This is the Green Bank Telescope. Or perhaps these arrays. This one is the Very Large Array in New Mexico. So we're going to talk a little bit about SETI, but I was first inspired by SETI, the Search for Extraterrestrial Intelligence, by a movie called Contact that I saw when I was about 13. And now I work through the Breakthrough Listen program at Berkeley SETI, doing just that, which is super cool to have something that inspired me when I was so young, getting to come back and actually do the science. So let's talk a little bit about what kind of signals are we looking for. So if you live in the Bay Area, you might have seen the Sutro Tower, or you might have seen a radio tower near you. And these can send off powerful radio waves that are detectable at a few light years away. We also send out these powerful radio bursts, kind of like radar, or like how a bat does echolocation. We're scanning the skies for nearby asteroids. So we have to make these loud radio pulses to make sure that we don't end up like the dinosaurs. And sometimes we use these high-powered lasers to help us with our astronomy to kind of correct for the distortion that our atmosphere gives us when we're looking at telescopes from the ground. So these are three ways that we emit detectable signals. So these are some ways that we are looking for detectable signals out there. We use a few different radio telescopes and an optical telescope to do our research. And we share the observing load with our colleagues. So we're all taking turns on observing with these big telescopes. And our group is also bringing on partnering with a whole variety of other telescopes. So it's a pretty exciting time for our group. And we want to see if we can use as many telescopes as we can to answer one of humanity's most fundamental questions: are we alone? So we're looking at 1 million nearby stars, we're looking at the galactic plane, and we're scanning galaxies as well. So this is a pretty cool time to get involved in SETI. And we release all of our data to the public if you're curious. So although astronomers, we have this pale blue dot, so I just want to go into a little bit of my research before we stop. So the Voyager spacecraft was able to go out and turn around and take a photo of Earth. But my question, my research is, well, what do we look like, not in the visible wavelengths that we can see with our eyes, but how about in the radio? So I'm working on a project called the Moon Bounce Project. So our radio signals emitted here in the white are traveling away from Earth, and some of them are actually being reflected by the moon. So I'm using our radio telescopes to point at the moon to listen for those reflected radio waves to come back into our telescope. So I'm trying to figure out, what do we sound like to an ET observer? So with that, I want to say thank you for taking this cosmic journey with me. We covered a lot of time and space, and hopefully we learned a few things today. And I think now I'll open it up for questions.
Yeah, sounds great. Thank you so much, Julia. That was amazing. I loved your demonstrations and everything. Excellent. If you could stop your screen share, perfect. All right. For folks learning along at home, we'd love to see what you're doing with this. If you do a follow-up activity from the family guide or educator guide, maybe you draw a picture or write a story or make a video, please send them to us by tagging @NatGeoEducation and using #ExplorerClassroom on Twitter. That way we can make sure Julia gets a chance to see all of your amazing work. All right, now it's time for questions. If you're watching online, send us your questions in the chat bar. We record them all, so once they're sent in, you just need to send them in once. And if you're on screen with me, get ready with a nice loud voice and I'll let you know when it is your turn. So I'm gonna start off with one from the chat, but then we have a lot of people joining us on screen today, so I'll get to them quickly. But a question that we have is, do you wanna go to space and why or why not?
Great question. Yes, I would love to go to space. Although it is a dangerous endeavor, I think by traveling away from our planet, you really learn how to appreciate what you have. I did this Mars simulation in the Utah desert where we pretended we were on Mars, and it just was so frustrating to not feel the wind in your hair and be able to feel the dirt and have to dress up in a spacesuit. You start to miss interacting with your environment. But I love exploring and I'm curious, so I think that would be a very cool adventure to go on, to go to space.
Awesome. All right, we're gonna go to Owen on screen. Let's see if Owen, I unmuted your mic. Go ahead and ask your question for Julia, nice and loud.
So about like which life forms you're searching for. What if there are life forms out there that like are not exactly not like humans on how they have to operate? They don't necessarily need oxygen. They've adapted to the environment that they're living in.
Great question.
You look for those.
Yes, that's an amazing question. So it's tough. So what we do know is life as we know it, and we know the kind of signals and biosignatures, the gases that we give off. But we are we're doing our best to also think about the unknown. So at least with SETI, we look for any sort of signal we call above the noise, any sort of strange signal that we can't explain by natural phenomena. And with these future exoplanet detections, there's a whole group out there that's trying to that's trying to look at different types of atmospheres. What we're also looking for is what we call a disequilibrium. Now, when you take chemistry class, you'll learn that when you put two things together and they react, they kind of come to a equilibrium. But we're looking for things that are out of balance, because here on Earth, our atmosphere is not in equilibrium because we have plants constantly pumping out oxygen. If we were to turn off all of the plants at once, we would know the oxygen would probably react with the carbon dioxide, and we wouldn't see that oxygen anymore. So even if it's not like oxygen, perhaps it's another molecule that is in a disequilibrium with its atmosphere, that we know something's funky is happening there. Great question. Hopefully I did a good job answering it.
Nice work, Julia. Owen coming in with a hard question.
I love it.
We're gonna go to another on screen. I'm gonna go to Jessie. Jessie, I've unmuted your mic if you can ask your question nice and loud.
I had a question. How old were you when this research?
Ooh, nice question.
I think everyone is born an explorer. So I would say probably as a little kid, I was doing, research in my backyard. How high can I climb before falling? That is considered, I would consider that research. But when I started working for more in research, in scientific research, I would say in college, I was probably about 21 or 22 when I started doing some research. Yeah.
Great answer. And then a follow-up question then from our chat online from Kira and Eli. How long did you go to school for to become an astrobiologist?
Great question. Okay, so I did 5 years of undergrad because I couldn't stop taking classes for some reason. And then I did a year of a master's, let me think. And I'm just about to start a PhD program. So I don't know what grade I would be in, like 13, 14, 15, 16, 17, 18. I'll be in 19th grade next year.
That's crazy. Good to start preparing them for all of that schooling. All right, we'll go to someone else on screen. We have Alejandro. I'm gonna unmute you so you can ask your question. Let's see. Perfect, go ahead.
Have we got any signals?
Great question. Yeah. We have not gotten any official signals. We haven't gotten any signs of intelligent life out there yet. There was one signal that was in the 70s, I believe, called the WOW signal, that there's a documentary out on it now that was a pretty loud signal, but we weren't ever able to hear it again. So I would encourage you to Google the WOW signal. But as far as SETI goes, that's about the most interesting one. But we're still looking. If we don't look, we'll never know. So great question. Yeah. I wish I had a cool answer, like secretly we found one, but I'm not supposed to tell anyone. But no, unfortunately, we release all of our data to the public, and we would be so proud to find a signal and share it with everybody. So fingers crossed for us.
I like the idea of not yet. We'll come back when maybe
Yes.
you find something. Awesome. We're gonna go to another online participant. We have McKenna. I'm gonna unmute you. Go ahead and ask your question.
Like, do you have any special tools you use?
Special tools. So we use these large radio telescopes that are bigger than the size of a football field. So those are pretty big tools. And I was mentioning those looking at rainbows. There's a special tool called a spectrograph, where it's basically like super fancy prism, where we can see those spectral lines. I think those are my two favorite tools.
Awesome. All right, we have more questions coming in online. Keep them coming, guys. From Jennifer Wright. She said, when did you want to become an explorer of space life? I know you mentioned the movie Contact, but anything else that kind of sent you this direction?
Totally. When I was about 5 or 6 years old, I went to school in Maryland at a public school. And for some reason, our public elementary school had a tiny little planetarium. I think we had this like great PTA team that was like, we're going to do this. So they got us a little planetarium. And as a small human, about 5 or 6, I was not this small, but I'm using my hands this way. Going into this planetarium, it blew my mind because I grew up next to a big city and it was hard to see the stars. So since about a young age, I've always been fascinated by the stars. And I was very lucky to have my parents to send me. We had the Air and Space Museum. We went to museums all the time. We went to astronomy nights. So I've always been into it, even as a little kid. And plus in the planetarium, they gave us stickers every time. So like stars plus stickers, like, sold. I was hooked.
That's awesome. I'm also usually sold on, if you give me a sticker, I'm sold.
So
all right,
easy.
On screen, we're gonna go to Rex and Evelyn. If you guys have a question for Julia, ask it nice and loud.
I have a question. Would life on a different planet be able to survive coming to our planet if it lives on a different one for its whole life?
Ooh, good question.
Yeah, that's a great question. So I'm going to start by asking if you knew that Mars and Earth and most of the planets, they interchange materials. So there are some scientists who think that perhaps life started on Mars and was kicked out through like a large impact, and a meteorite from Mars landed on Earth and perhaps seeded our planet with life, or perhaps vice versa. So it depends, I would say. We see these forms of life on Earth called extremophiles that can survive really harsh conditions, like even high amounts of radiation, freezing temperatures, boiling temperatures, things like that. So perhaps if there's extremophiles on another world, they might be able to survive on our planet. I don't know if you've heard about tardigrades, but those little critters can survive in the vacuum of space for 10 days and come back to life. It's just crazy. So maybe we'll have some interplanetary tardigrades.
That's awesome. We're gonna go to another of our on-screen students. I've got Savannah. I've unmuted your mic, hon. Go ahead and ask your question.
Has there been any signs of the hydrothermal vents on either of the moons you were talking about earlier?
Ooh. So we haven't been able to go through the ice yet to see if there's any hydrothermal vents, but we do know that there's some sort of heating happening to keep the ice warm enough to melt into water. So we do know there's some sort of thermal aspect to the moons that is warming them up enough to create liquid water underneath the ice. But yeah, we don't know if there's hydrothermal sea vents under there, but that'd be a great field to get into. And I know that there's some concept missions out there that they want to maybe melt or drill through some of the ice and send a tiny little submarine to swim around and take photos and videos. Wouldn't that be so cool?
That would be amazing.
Yeah, sign me up.
All right, another question from online from fifth graders in Fresno, California. You answered one of their questions about life on other planets, but have we ever traveled to another galaxy?
Ooh, well, we haven't even sent humans beyond the moon, and the farthest spacecraft that we have sent has recently left our solar system. It's a little bit of a tricky concept, but the Voyager missions that I was mentioning in the beginning have reached what we call interstellar space. So we haven't even had spacecraft leave really our immediate neighborhood. So no, we haven't explored any other galaxies, but we do explore them with our telescopes. We just haven't sent anything out there.
Awesome, great answer. All right, we're going to another on-screen student, Lariah. I've unmuted you if you want to ask Julia a question.
What happens to the radio waves when they enter a black hole?
Ooh. Well, so black holes are so powerful that not even light can escape. So I would assume that not even radio waves could escape too, because they're going the same speed. But that's a great question. I don't know if I've thought about that question. Yeah. I don't know. I'm not an expert in black holes, but I hear they suck.
Maybe Lariah, that's something that you can investigate. Awesome. All right. Well, Julia, we're coming towards the end of our time with you. So our last question, do you have any advice for young explorers out there watching today?
Absolutely. My favorite advice is just to stay curious. I think you can make anything super interesting just by having curiosity and asking, well, why is it that way? How do we know? How did we find that out? So I'm always trying to look for my own answers, and even, when I'm on a walk going to iNaturalist and taking photos of trees I've never seen before, and trying to figure things out. So I'm a person that really likes to know what my surroundings are like. So I would say stay curious, and that will set you up for success in being whatever kind of thing you want to do, whether it's scientist or an artist or musician or what have you.
Awesome. I think that is a fantastic note to end on, to stay curious. For all of our explorers out there, check out Explore Classroom and many, many more educational resources at natgeoed.org. We hope to see you at our next events. Starting again next Monday at 2 p.m. Eastern, we'll be with Jennifer Kingsley, who will talk to us about her adventures in the Arctic. All right, all of our students online, I'm going to unmute all of you so you can do a nice big thank you and goodbye to Julia on the count of 3. 1, 2, 3.
Thank